Well, let's just recap what we've found out about calculus so far. We've found a lot of things it's going to be useful for without actually finding out how to do it yet. We'll get there. But first, let's recap then. We found that calculus is talking a lot about gradients. But unlike in coordinate geometry where we were restricted to linear functions that were just an equation of a straight line, with calculus we can find the gradients of quite complicated curves. How do we do that? We just plot a straight line, the tangent, at each point. So the gradient is found by first finding the derivative of the function. And that's a way of finding the gradient of the tangent at each point around the curve. So at each point, what can we do? We can find the gradient. We do that by substituting the value of x we're interested in into this derivative that we found using calculus. Once we know the gradient, we can find the tangent at any point on the curve. We'll know the point on the curve, we know the gradient from the derivative, and then we just use our coordinate geometry formulae. We're good at that. We've got lots of experience doing that. Similarly, if you know the tangent, you can find the normal at a point. We've done plenty of examples of that before as well. Again, if you know the gradient of the tangent, you can quickly find the gradient of the normal. And then it's just a straight coordinate geometry problem. What are we going to be using this for? Very good for finding local maxima and minima, because at those places we found the gradient is always zero. And gradient in calculus, remember, is the derivative. So once we know how to find the derivative, we will just put that equal to zero, and that will give us these maxima and minima. That lets us do some modeling to find optimization, because the optimal solutions are just either the maximum or the minimum. So once we can do this, we can straight away do this. And another useful application of the derivative is understanding that as just the rate of change of one variable, typically your y, with respect to x. So the rate of change. That's what a gradient is. It's the rise over the run. How quickly does y change as x changes? The beauty of calculus is it gives us an equation for the rate of change rather than just a number all the time. Once we've got a formula, we can put values in to get a number, but it's nice to have that formula to start with, which we don't have with just coordinate geometry. So that's the beauty of calculus, enabling us to work out very quickly gradients and then lots of applications of that. Okay, now it's time to learn to do this differentiation process to find the derivative. Well, let's give you some examples just to show you what happens again visually before we launch into the algebra of it, which isn't so complicated, but I think it's nice to see this first. So here's a function we've got. Again, it's a cubic function, and I've simply asked in one line, I've asked GeoGebra to give me the derivative function of this original function, and here it is. Do you recognize anything there, I wonder? So the black is my original function, and the red is the derivative of that black function. What sort of shape is the black? We call it a cubic. What do you think that red one might be? It's a quadratic. Okay, that's a wee bit interesting. Then again, one more line. I asked GeoGebra to give me the derivative of the red one. Let's have a look. Oh, well, you know what that is. Okay, so we differentiate a cubic, we get a quadratic. We differentiate a quadratic, we get a straight line. And what if I differentiate that particular straight line there? I get Now that's a bit strange, is it? We'll talk about this more in class, but it's not as bad as it looks, because this is a particular type of straight line. There's something special about this green one. So in general then, let's get rid of the mess. If we differentiate a cubic, we get a quadratic. If we differentiate a quadratic, we get a straight line. If we differentiate a straight line, we get a particular type of straight line, and that's what we can explore more in class. Okay, so that's visually what's going on. Now I want to show you a table of some derivatives. So this is it. We started with the cubic here, and we would have got a quadratic. If that were the cubic, it wasn't. It was a more complicated formula I had. But if I just plotted f of x, or y equals x cubed, my derivative would have been the quadratic 3x squared. Okay, so here's a table of derivatives. And once you can see this pattern, you're going to be able to differentiate so many different problems. So I want you to look for the pattern here. If I've got my original function as y, or f of x equals x to the fifth, the derivative, and the notation I'm using here is f dash of x, is 5x to the fourth. Going down a line, if f of x is x to the 4, f dash x, 4x cubed. fx equals x cubed, f dash x, the derivative, is 3x squared. You can probably see that pattern. So you can probably quite quickly, I hope, do the next next cell in the table. Can you fill in this one for me? Okay, so if that's going well, what happens here? That might take you a little time to think about, but I really want you to have a go at that. Because if you can get that and that, then you've just about got differentiation. You've seen the rule, you can then go and do all sorts of problems with it. But just to check, make sure once you think you've seen the pattern that you can do x to the 12. Try that. So I'd like you to make some attempt to fill in each of these three cells here. Try and see this pattern. Once you've got that, we're away doing gradients of functions, finding tangents, finding normals, finding maxima, minima, optimal solutions. We can do the whole chapter. So fill out that table and we'll see what you came up with when we get together in class.